Good morning, my dear students. I'm Sridhar sir, your physics teacher. In today's class, in the ray optics, we are going to discuss the prisms. So first, we'll start with the theory involved with the prisms. So as you have encoded in the previous class, we had the discussion about the total internal reflection. Now the next part of the ray optics will be the prisms. That one. So basically, if you look at the prisms, like what is the use of this? Why do we use these prisms? Hmm? What is the purpose of this one? So if you look at the various optical instruments like telescope, binoculars, microscope, periscope, hmm, we do use prisms to invert the images or to split the light. If you want to break up the light into its components, we can use prism, or it can be used also like a optical filter. So these are the various applications are there. So in what we focus more on the basic ideas of the prism and its applications. So let me start the class. Our topic will be the prisms. So let me begin. What is actually prism, that one? So here, let me show that. So this will be the prisms which you are seeing it. Hmm? What I am showing is a, triangular prism. That one. Huh? I think it's visible properly. Yeah, triangular prism. So you have the refracting edges, and I'll make it. No. What we are discussing this is the prism. So we have here the refracting. It's a triangular prism. So it will have the refracting faces. This will be the refracting edge. These are the refracting faces. This will become the base of the prism. Okay, I think it's clearly visible. This is the base of prism. So these are the refracting surfaces. This will be the refracting edge. So when a light passes through it, if a white light passes, it will split up. And if a monochromatic ray of light passes, just gets deviated. So these are the two major purpose of this particular prisms are there. Okay, let me get into the this one. Okay, first we'll start with the basic the prism. How prism will be. Triangular prism is what first we'll discuss. Okay, this part will be the base. Huh? This will be the called as base of the prism. Rough diagram. What we are discussing is a triangular prism. Okay, that one. So this will be 1, 2, 3, 4, 5, 6. So this 1, 2, 3, 4 and 3, 4, 5, 6 are refracting surfaces. 4, 3 is called as refracting edge. Okay, fine. So fourth is called as a refracting edge. So this particular thing is called as a refracting edge. So these are the refracting faces, surfaces or faces. So what do you mean by refracting surface? So there's a one refracting surface. So like this, basically, we will define the prism. So what is the basic way of describing a prism? Is a transparent medium bounded by any number of surfaces. It can be plane or curved, such that the surface on which ray incident and surface through which ray emerges are plane and non-parallel. Okay, fine. So this is the basic idea of the prism what we. So what do you mean? What is the? I wrote something here. So this is the like a ray which enters here. So it will be incident on a plane. Okay, fine. Here the ray will be incident. It will undergo refraction. Then this one. Again it will emerge. So it will emerge to again another surface. This is the refracting face, that one. Two refracting faces, the angle between them will become angle of prism. What is A? A is called as angle of prism. So the angle between the refracting edge, refracting faces is called as angle of prism, and this will be a plane diagram. This will be this will be the three-dimensional, and what we discuss most of the problems will be a triangular prism. Our syllabus will confine ourselves to the triangular prism. So now the plane view, this will be three-dimensional one. So what you are viewing is 3D view. This is plane view. Or 2D view. If you stand here and start looking at this one, no? So you can see only the face 1, 4, 5. That's what here. Got it now? So what Prism basically does, so it is having only two purposes, nothing big, that one. It is having only two purposes. It function like a basic function of Prism. Basic function of Prism. So what it does, it changes the direction of ray and breaks the chromatic light into its constituents. This is called like a dispersion. Changes direction. So it is having basically two purposes. You can see one, changes direction of ray, and next is the dispersion. So all our applications will be based on only on these two parameters. There's a basic function of a prism. Why do we use prism? Is if I want to change the direction of ray of light, I should take help of the prism. Or if I want to break up the white light into its colors, or dispersion, what we call, to disperse a ray of light, then we should take help of the prism. So it should be transparent, it cannot be opaque, it should be made up of this one. So now few things are there we will define. So first, refracting phases. Already I defined. Once again I'll bring it. Refracting phases. So what are refracting phases? The plane surface, the plane surfaces which face which faces incident and emergent. Emergent rays. So these are refracting phases. So next, refracting edge. The diagonal angle between two refracting phases. So we are not understanding something you are writing. Okay, I'll bring the same diagrams. Let me bring that. Let me bring this also. Okay, what all I'm giving explanation is related to this. So it's telling like what are the refracting phases. So already I told you like a 1, 2, 3, 4. This will be refracting phases. Similarly, 3, 4, 5, 6. This will be other refracting phases. So where the incident ray, no. So where the incident is incident, it is incident on the surface 1, 2, 3, 4. This is one refracting, and the emergent ray is at 3, 4, 5, 6. So these are the refracting phases. Then refracting edge. This is the refracting edge. Okay, fine. So this will be the refracting edge. It is called as. So the diagonal angle between two refracting faces is what? Angle of prism. So here I'll indicate. Here. So what is the angle of prism? Sorry, refracting edge. The diagonal angle. This is the angle of prism. No? Okay, the refracting edge. I'll define it. Where the two refracting faces meet. Where the two refracting faces meet. Okay, fine. So here is what the refracting faces, they'll meet here. So this called a refracting edge. Okay, so these are the some very essential part of the prisms what we are discussing. Then we'll go for the types of prisms. The next, the idea is So types of prism. So usually what all we discuss is our syllabus is related to, we will discuss this. Okay, fine. So we will discuss this one. Square prism, rectangular prism, pentagonal prism, hexagonal prism, octagonal prism. It can be of anything, prism, that one. Okay, now, so like how you are calling this as a prism. So let me bring only the plane view. Suppose if this is the ray of light is incident. It will undergo refraction. You can see, so this part is what we will take for the analysis here. This is square prism. Still, what all we learned, triangular prism, the same ideas are being applied for this. Okay, no? So the ray will be, I'll just show the, okay, this one already triangle prism. Area of light will come here. So it will undergo refraction, moves from denser, rarer to denser, will bend towards normal. This dotted line is toward normal. So it will emerge out. So it is changing. So what this prism, triangular prism does, it will change the one, I'll write it. So it will change the direction of path. So now what about the rectangular prism? So it will be of this kind. So this will be two. Like this we can go for rectangular prism. The rectangular prism will be, again the idea will be same. So here the ray of light which is incident here will undergo refraction. Let me draw it properly. Okay, this is the rectangular prism. Then pentagonal prism is what, this one. Pentagonal, how many five sides are there? Let me try. I do have pentagon. Yeah. So here also I can bring the idea of the ray of light which is incident will undergo refraction. Okay, fine. The idea is same, like, so what all these prisms will do, they just bend the ray of light. They're just used to change the direction of propagation of the ray. You want to change the direction of path of the ray of light, then take help of the prism. So the plane view, so this will be the, not only this, so we can, okay, there's no much difficulty. I can't draw that octagonal prism. So let me just show that one. So sometimes we discuss some problems of this kind. Maybe sometimes we do encounter. So you know to bother. So what all we discuss, the triangular prism, those same ideas will be applicable for all these remaining types of prism. So that's why we'll just focus. Our syllabus will be more priority will be given to the this triangular prism only. Okay, fine. Okay, now we will get into the this will conclude the story part. No. So every time doing analysis for this three-dimensional will be very difficult. So therefore, we will consider the principal section. Means when a ray of light is incident, it will be incident at somewhere at this particular point. No. So there I'll draw a perpendicular called as principal section. We will define like this: principal section. So what is this one? The section of prism by a plane perpendicular to the refracting edge and contains incident and emergent rays. Every time this three-dimensional analysis will be very difficult, so therefore we'll go for plane diagram. So the ray will come and strike at one specific point. So from there I'll drop a perpendicular to the refracting edge. So that particular plane is called as a principal section. So the principal section usually will be a plane which will be perpendicular to the refracting edge and that contains the incident and emergent. So what I'm showing, this is a what you say two-dimensional view. Then nothing but the principal section of this particular following prism. For square prism, this will be principal section. For rectangular prism, this will be principal section. So this is the usually typical terms what we get and we are using them. Okay, let's go for to study the deviation of the deviation produced by the prism. So we'll derive an expression for the deviation produced by a prism. This will be our topic. So let's try to calculate the deviation produced by prism. So I'll be picking up a triangular prism and its principal section is what I'll be showing it. A ray of light is incident here. This will be the normal. So after refraction, so this is the incident ray, refracted ray, this is the emergent ray. This is the angle of prism A. Now let's get into that one. So what are the principal sections? So I'm again showing a principal section of a triangular prism. This is what is this diagram? Principal section of a triangular prism. So this particular thing is an incident ray. It is monochromatic. What we discuss is monochromatic. Monochromatic monochromatic incident ray. Let the angle of incidence let it be I1 and this is the normal N1, this is N2. Let this angle of incidence be I1. This is the refraction angle. So let this be medium A, this air. This is the glass where refractiveness of prism let it be mu. No. So the incident ray will make this the boundary, and this will become the normal. Hmm? And the angle between normal and incident will be angle of incidence I1. This will be the refracting angle. As the ray moves from light to denser, so it should bend towards normal. So as the ray traverses a path, again it will encounter one more boundary. Now this will become the normal. This will be the normal for this particular surface. Some rough diagram I'm showing. So here now the ray is moving from denser to denser, should bend away from the normal. So let this angle of incidence, let me call a refracting angle. Though its angle of incidence, I'll use symbol R2, not I2 something. And let this emergent angle, let it be I2. So this is the refracting angle. The symbols is what I2 I'm using here, this one. So what will happen to the ray now? The ray which I wanted to go, did it undergo any deviation? Yes, it is. This is the deviation. Delta is what I'll use for deviation. So in the absence of the prism, the ray would have just traversed this dotted line path. Now because of the presence, due to presence of prism, the ray is now this is the emergent ray. This is the emergent ray. So the ray will take this particular path here. This is called a deviation. So it got deviated. Say I'm able to change the direction of path of the ray. I'm able to change the direction of path of the ray. Now, what did they say? A is called as angle of prism. This is the refracting faces. What we are seeing is the principal section here now. I'm just interested to measure this deviation. So, what quantities usually I know? I know the deviation. I wanted to express this deviation in terms of angle of incidence I1, mu, and angle of prism. Let's try to get expression for this. Before this, we do have here a, I'll extend back this. A, so this is M, O, B. So this is the angle A. So this you call say some phi something. Let it be here. So we have cyclic quadrilateral. Cyclic quadrilateral A, M, B, N. In cyclic quadrilateral, the sum of opposite angles should be equal to 180 degree. So therefore, A plus phi should be equal to 180 degrees. So in the triangle, regular triangle, MBN, R1 plus R2 plus phi equal to 180 degrees. So equating these two, so this A should be equal to 180 minus phi. So there's R1 plus R2 equal to 180 minus phi. Substituting this is the equation 1, equation 2. So therefore from 192, R1 plus R2 equal to, there's a one equation you do remember, very important, almost at many places this will come. How these two angles are related to angle of prism given by this one. What is R1? R1 is the refracting angle, R2 is the incident angle at the second phase. So now after this, we'll apply the Snell's law at the first and the second phase. Applying the Snell's law. Sine I1 equal to mu sine R1. Similarly, mu sine R2 is equal to sine I2. This medium is air. The surrounding medium, let it be air. The refractive index of the material of the prism, let it be mu. So applying the Snell's law here, sine I1 is equal to mu sine R1, mu sine R2 is equal to the sine I2. What we have to calculate? We have to calculate the net deviation delta. Call from Ravinder Reddy Free Homes. We have to calculate the net deviation suffered by it. So the deviation suffered, the net deviation, this should be equal to deviation at m plus deviation at n. Deviation at m plus deviation at n. Deviation at m will be the ray wanted to traverse this particular path, but it got deviated. So I1 minus R1 should be the deviation. The deviation suffered by the ray at the first phase will be angle of incidence minus angle of refraction. Then this is the angle of incidence, this is the angle of refraction or angle of emergence, what you can say. So the ray wanted to traverse path like this here, but it got deviated. So what is the deviation at this point will be at the emergent phase, I2 minus R2. This is a deviation. So therefore this deviation is equal to I1 plus I2 minus R1 plus R2. So substituting this I1 plus I2 minus it. So this is the expression for deviation in terms of angle of incidence and emergent angle and this one. So this I2 will eliminate. I1 I'll be knowing at what angle the ray is incident on the prism. This I2 has to be eliminated here. So for that, what happened? We will take help of some mathematics here. So first we will start with the mu sine R 2 is equal to sine I2. So therefore, what is I2 is equal to sine inverse of mu sine R2. So this will become R2 will be A minus R1. Further expansion of this will be I2 equal to sine inverse of mu sine A cos R1 minus mu cos A sine R1. All this will become sine inverse of mu sine A cos R1 will be root of 1 minus sine square R1. Sine R1 will be sine I1 by mu. So the expression for I2 will be sine inverse of sine square R1 will be okay, this is the expression for the deviation. Sorry, the angle of incidence. So the net expression will be the deviation should be equal to now I1 plus I2 is this much. Let me adjust it properly. Okay, fine. So this will be minus of E. Okay, there's the expression for the deviation suffered by the incident ray due to the presence of the prism. Okay, I'm showing it completely now. Yeah. So what is delta? Delta, you have to go to columns. So what is the delta? Delta is called as a deviation. So the deviation suffered by the ray of light is given by this particular. What is I1? I1 is the angle of incidence. N1, N2 are normal at the incident and the emergent phases. Now let's plot this deviation as a function of angle of incidence. Then we'll see that what conditions will arise. So we will take the deviation as a function of this angle. Hope everyone, this will be very simple. Just we took help of this equation, the deviation equal to I1 plus I2 minus A. This I2 is what emergent angle. This I2 is what should be replaced here, no? Because the deviation I should bring in terms of I1. So how to replace I2? First I'll mu sine R2 is equal to sine I2. Then I2 equals sine inverse of mu sine R2. So what is R2 is equal to A minus R1. I'm replacing this. Hope you'll get it. Then sine of A minus B formula, applying that. So I'll end up this formula. Finally, I'll get expression for deviation. So when I plot this deviation as a function of angle of incidence, the curve will be okay, this will be the deviation. So this will be the minimum deviation. There's some other colors we'll use. Not visible. Huh? I'll make them visible. You can see now. So this will be the maximum deviation, minimum deviation, and the deviation as a function of angle of incidence according to this particular equation. We have plotted deviation as a function of angle of incidence. On y-axis, deviation. On x-axis, there's an angle of incidence. Then how the curve will be? The curve will take shape like this. It's not a symmetric, you can see that. It's not a symmetric curve. Are you looking this one? It's not a symmetric curve. So if at one specific angle of incidence, the deviation will be minimum. Huh? And there are two angles at which the deviation will be maximum. So we have to just calculate all this maximum deviation, expression for maximum deviation, minimum deviation, and at what angles the deviation will be maximum. That will be the next part of the discussion. So the complete description, I'll bring it. Yeah. So what all we have discussed here. So as what is I1? What is I1? I1 will be selected. This will be 0. So when it is along N1, it will be 0. As I keep on increase angle of incidence, then the deviation at what happen? It will start from one angle, maximum, then decreases. And at one specific angle of incidence will be minimum, then again it increases, again it become maximum. So we have to calculate what are these angle of incidence at which deviation is maximum and at what angle the deviation will be minimum. Now you can ask question, sir, what is use of this? The refractive index of material of any material is a very difficult quantity to measure, this mu. If I can measure this minimum deviation, I can calculate the mu of a prism, mu of metal of the prism. That's the main purpose of why we are studying these things. Later we'll go for applications. Okay, now, so what is our next target is like how to get expression for this minimum deviation. So we'll take help of this particular formula. I'll start from here. Okay, well, so next is expression for minimum deviation. Now the D expression for deviation will be sine inverse of mu sine R1 plus okay, so some of you are getting confusion. I will start with sine I1 equal to mu sine R1, mu sine R2 is equal to sine I2. Solving this, we got expression for I2 as yeah, this particular thing. Let me use this part. Let me substitute all these things. Deviation is equal to I1, I can write it as sine R1 Okay, let me differentiate this with respect to R1 because I have to calculate the minima. Differentiating about deviation with respect to R1. Differentiating respect to R1. So d R1 is equal to sine inverse of this will be sine square R1 minus mu sine inverse of x. This will be x root of 1 minus, so mu cos of a minus R1 by root of mu square sine square a minus R1. How we got it? First I'll differentiate sine inverse. Sine inverse, everything this will be x. So what we write dx by root of 1 minus x square. Then again derivative of sine R1 will be cos R1. Okay, for this for minima what is needed? The first order derivative should be 0. For minimum this should be equal to 0. So this will be 0 only when a minus R1 this is possible only when cos R1 and cos R2 are should be positive, no? Or we should better say like this is possible only when these two square roots are positive. So above condition is possible only when roots are positive. So therefore, for the roots to be positive, what are the only when square roots are positive. So therefore, what is the basic necessary condition? R1 should be equal to A minus R1, or 2R1 equal to A, or R1 equal to A by 2. We know that R1 plus R2 equal to A. So substitute R1 equal to A by 2. So R2 is equal to A by 2 negated. So what is the condition for minimum deviation? R1 equal to R2 equal to A by 2. Similarly, I1 equal to I2. We know minimum deviation I1 equal to I2. I1 plus I2 minus A. So therefore this will be I1 plus I1 minus A. So minimum deviation equal to 2I1 minus A. What is I1 equal to? Delta minimum plus A by 2. R1 equal to already we written A by 2. So let me take help of these two ideas. Let me apply the Snell's law. We know that sine I1 is equal to mu sine R1. Let me substitute the value of I1. Sine of delta minimum A by 2 equal to mu sine A by 2. So what is the mu of prism? Sine of delta minimum A by 2 by. This is something very important. Like a, can I measure delta minimum in a lab? That's very easy. You can, with your eyes, you can able to measure that minimum deviation. When you keep the prism on the prism table and as you rotate, hmm, so you can clearly see that the ray will get minimum deviation. And you are able to measure delta minimum. You know angle of prism. You will get the mu, the refractive index of the material. This is the main idea of the prisms. Like why do we use minimum deviation? To just predict the refractive index of the material of the prism. That's the main purpose of this mu. Getting the idea? This one? So what we can write here? We can easily measure in a lab. So as you can measure easily delta minimum and the angle of prism. So the mu of material of prism, what happened? We can calculate using this particular formula. So the what is the major application of this particular formula is like a, you can measure the with the minimum deviation you can measure the material of the prism, that one. So what is actually what happens in the minimum deviation? Next idea. A few questions like what actually happens at minimum deviation. I will take the prism. So we are not understanding what is actually that minimum deviation. If this is the prism, if this is the ray incident, The ray wanted to traverse straight here. This is the minimum deviation. One more. This is what that minimum deviation. This is the incident ray. Refracted ray. This one. So how the refracted ray? The refracted ray will be parallel to the base of the prism. This is the base of the prism. At minimum deviation, this is what happens. And out these two are, they will be parallel. The refracted ray inside the prism will be parallel to the base of the prism. So at minimum deviation, the refracted ray will be parallel to the base of the prism. And these two angles will be equal. Let me write only I. Don't have this. I'll draw another one. Yes, yeah, now this will be the, okay, I think, yeah, this was our diagram. Fine. So this will be the, and these two will be symmetrical. The incident ray and the emergent ray will be again symmetric. This will be symmetric. The emergent ray will be symmetric to the incident ray. The ray wanted to traverse this our minimum deviation. The ray wanted to propagate along this green color dotted line. Due to prism, it will undergo the deviation, and the deviation will be minimum. At minimum deviation, the refracted inside the prism will be parallel to the base of the prism. This is one very basic idea. So these are very important. At minimum deviation, the refracted will be parallel to base of the prism. I think I'll conclude this thing. Incident angle is equal to emergent angle, where E is nothing but I2 only. I just change its symbol, and these two angles will be equal again. R1 equal to R2. So what is the main purpose of minimum deviation? Why we use in the lab? To find out the refractiveness of material of the prism. So like this, we will started with a small idea with the minimum deviation one. Next, we'll go for the maximum deviation one. Okay, now kids will go for, after learning the minimum deviation, we'll go for the maximum deviation. Already we have brought the expression for deviation, and this was the particular curve, the deviation as a angle of incidence. We just discussed the minimum deviation. So what is this deviation? So let me just once again brush up. Here the ray after undergoing Okay, this is the emergent ray, this is the refracted ray, this is the incident ray, angle of prism. So the deviation, what we were discussing is this is what the deviation with the red color I will show it. Fine, at least now you are able to understand, and this is what that angle of incidence. R1, R2. This is the emergent angle. E I'll write it, or I2. This is a deviation. Okay, got this? Now we had the discussion on the minimum deviation. Now we'll focus on this maximum deviation. We know the basic deviation formula. This is our formula: I1 plus I2 minus A. The deviation, in fact, will be maximum when I1 equal to pi by 2, because the deviation when I1 equal to pi by 2, the deviation will be maximum because the deviation depends on I1 and I2. When I1 equal, what is the maximum possible value of I1 is equal to pi by 2. The maximum possible value of I1 will be 90 degrees. Then the deviation will be maximum. So here we'll first put like deviation will be maximum when I1 is equal to pi by 2. So therefore the maximum deviation will be pi by 2 plus this E, I'll write it. And I2 is called as E minus A. What is E that we have to calculate? So how do we show this? So it will be grazing incidence some angle. Okay, just follow the diagram. It'll be much easier. So this is what I1, and this angle is what E. This is R1. Okay, fine. This is grazing incidence. So what is the condition? It's grazing incidence. Now you can ask questions, so like, okay, this angle is 90 degree and this is a normal. Why do the ray will undergo, why the bending will occur here only? Why can't it just trace out, why can't it just graze this refracting phase? Why it will bend here? See, the idea is here on paper 90 degree, it will be maybe 89.99 degrees. The ray will be here. Will undergo refraction at the point where it is incident on a face. On paper, 99.99 what you write equal to 90 degree. If it is really 90 degree, the ray will just graze the refracting face this one. Why do it will bend here? So practically what will happen, this will not be 90 degree, it will be 99.99 degrees if the ray will undergo refraction. Again here it will undergo refraction here. And this angle is called as the emergent angle. This is what we should calculate. Because I know I1 is pi by 2. This E has to be calculated. Now come for the TIR. For if the incident ray grazes the grazes the boundary, then the angle of refraction should be equal to critical angle. So this R1 will become now critical angle. Then this will become A minus C. So we are not understanding. So we know R1 plus R2 equal to A. No? I'll write all these things here. What happened with Prism? I will redraw it. Okay, this so R1 plus R2 is equal to A. Look at the diagram. Looking at the diagram, R1 plus R2 is equal to A. Then uh, I'll do one thing. I will write all these things nearby. Later on I'll bring it. So what is R1? R1 equal to critical angle. So what is R2? So we'll write it. R2 equal to A minus R1. And we know R1 equal to critical angle. So this will become A minus C. So now we will write the Snell's law equation using Snell's law. Mu now using Snell's law, it will be mu sine of A minus C. Here. Mu of sine of A minus C should be equal to sine E, because what is the other medium? The medium on either side of prism, it is air. Can we replace E now? So this will be what is sine C? Sine C should be equal to 1 by mu, because the medium on either side of prism is like a rare medium equal to air. So refractiveness of air will be 1. So sine C will write it as this E is equal to sine inverse of mu sine A. So substituting this in expression for delta max, so the maximum deviation, I got the formula pi by 2 plus this one minus E. This is that expression for maximum deviation. When do that will occur? At pi by 2. When angle of incidence is equal to 90 degree, then the deviation suffered by the ray will be maximum, and how much that maximum deviation depends on this quantity. So we have just brought an expression here. So when the deviation will be maximum means when angle of incidence equal to 90 degrees, what we are giving here. Okay, fine. So there's one thing. So now definitely you can ask, sir, what about this angle? Means now as 90 degree, when angle of incidence is almost 90 degree, the deviation will be maximum. So sir, can you show that deviation, maximum deviation? You are supposed to show that. Okay, we'll do one thing. I'll extend this line. This is the deviation, maximum deviation. I'll take it off this. The ray was the incident on the first phase at a grazing incidence, undergo refraction, and will emerge out. So this is the now this particular deviation, what we'll call this a maximum deviation. How much it is, it depends on these things. The below formula is there. Yeah. Then at what should be the angle of incidence? 90 degrees. I want this particular angle. From principle of reversibility of light, if the ray of light is incident on this phase, then it will retrace path, no? Then also the deviation will be maximum. Then this will become angle of incidence. This will become angle of emergence. So, sir, we are not understanding. From principle of reversibility of light, if the incident ray first strike this phase at an angle of incidence E, then it will retrace path, no? So I'll draw the diagram better. Everything I'll show in one specific frame. If the incident ray so after refraction, I should not show parallelities. Then it grazes like this. No, this will become angle of incidence, no? Let it be as it is the symbol. So this will be 90 degrees. Critical angle, A minus C, this angle. I'll give this is the incident ray. Now look at the ray now. So what is that angle? Other angle. Other angle should be E. That's all. And what is that E? We have brought this expression. Okay, are you getting now? There are two angles are there now. One angle where if it is equal to E, if the angle of incidence equal to E, the deviation will be maximum. And the other angle will be at 90 degrees. So, sir, like we are getting confusion. So, just shall I put one simple thing? For grazing incidence, grazing emergence, the deviation will be maximum. Means, sir, like, can you show them in one diagram? It will be easy for us. Everything can you put in one diagram? Hmm? Okay, we'll exhibit everything in one diagram. For grazing incidence, I1 90 degrees, this is critical angle A minus C, this is emergent angle, and the deviation is maximum. Okay, fine. Okay, I'll show this arrow like this. Now, what about if angle of incidence equal to emergent angle? This will be very, very important, the discussion. You see now, this is the some emergent angle, and there will be grazing emergence. There's actually the beauty of this particular topic. The angle of incidence is E. This is critical angle. Here A minus C. This is A. This is 90 degree. The deviation will be maximum here. So can you show that deviation? Where you show that deviation? You can see this is the deviation. Huh? Here this is a deviation. So for grazing incidence, and here grazing emergence, the deviation will be maximum. For grazing incidence, deviation is maximum. For grazing emergence, okay, hope everyone is able to understand. These conditions are very important. So that particular graph was here. I'll bring that graph also for you. And how much value of that also we know it. This is the E. Okay, and the curve is not symmetrical. This angle is not equal to, you can see this part of the curve. These two are not symmetric. If you measure this angle, delta theta 1, delta theta 2, greater than delta theta 1. Okay, the curve should not be symmetrical. So you should not show these two parts as symmetric. So there's a basic idea of the maximum deviation concept. Minimum deviation, maximum deviation. It's having its own applications. Huh? This one, maximum deviation also. Next again, a condition for no emergence. One more last theoretical topic. We'll discuss this. Condition for no emergence for any angle of incidence. Suppose we have a prism. If this is a prism, the ray for any angle of incidence. I'll first draw the diagram, then you will understand what actually I am trying to explain. For any angle of incidence, the ray what happens should not emerge out. Let me use this color. Here, this is one angle. It will undergo refraction and will undergo TIR. I'll send another color ray. I'll, this is ray 1, this is ray 2. So what's happening to this one is, it should not emerge from the other surface. A ray is incident on a prism, but it should not emerge from the other surface. So condition for no emergence. So what is the maximum upper limit? Will be 90 degrees. For any angle of incidence, the ray should not emerge from the other surface. Then what is the basic necessity condition? So let mu be the, oh, 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 why it is. I'll bring again. Huh? Okay, fine. This is our discussion. Angle of prism. So what is the basic necessity condition is, for any angle of incidence, anywhere from 0 to 90 degree, the ray should not emerge from the emergent surface. So what is the basic necessity condition for this? These things is what we are discussing. So how that angle of prism, refractive index of the prism are related is what we are trying to search here. Should not emerge means what should happen to the ray? Should undergo TIR here. So again, I'll bring the necessity condition like this. The ray should undergo if for a grazing emergence, so now it should, if the ray undergoes TIR at the emergent surface, then definitely what will happen, so it's as good as like it is not emerging out. Then for grazing emergence, what should be the incident angle? The incident angle should be equal to critical angle. For any angle, it should be anywhere angle from 0 to 90 degree, the ray should not emerge from the other face of the prism. So what is the necessity condition for this? So this should be the critical angle. Then only this angle will be 90 degrees. So how to bring the condition for no emergence? So what we are trying to derive the condition for no emergence here. For any angle. What is the maximum permitted angle? It should be 90 degree, no? What is the maximum permitted angle? It will be 90 degrees. So, sir, is for this to happen, what is the maximum permit? For 90 degree itself, if it undergoes TR, means for any other smaller angle, it will undergo TR. So definitely, I think this is not a condition. Huh? Just I'll bring the proper diagram. No, you see this. For ray, if it comes like this, then it will undergo TIR. If this is 90 degrees, then this should be the critical angle, A minus A, this is mu. So what is the basic necessity condition? This angle of incidence here should be greater than critical angle. If it is equal to critical angle, there will be a grazing emergence. Greater than critical angle, then it will undergo TIR. So what is the necessity condition? The ray must undergo TIR here. Here it should undergo TIR. So therefore this angle should be greater than critical angle. Therefore, so we know sin C equal to 1 by mu. Like this, we'll put a condition. So now what will happen for, if for 90 degree itself it will undergo TIR, means for any other smaller angle it will undergo TIR. I'll write it here. This is the condition for no emergence. So like this, the check the will there be emergent ray or not? Who will decide? It all depends upon this particular thing. So for any problem, you must first verify this particular data. Is it A greater than or equal to? If A greater than or equal to 2 sine inverse of 1 by mu, the ray will not emerge from the other face. If it is less than that, the ray here will undergo refraction, will come out. I think there's one more necessity condition which you have to be very careful when you are dealing with some problems here. Okay, this is about the basic theoretical idea about the TIR. So first we brought the deviation, and then the minimum deviation, other things. So one more last for small angle prisms. Okay, I think I'll explain in next class. Okay, kids, like in today's class, we had a discussion on the prisms theory. So first, we had a discussion about the different types of prism. What do you mean by prism? This is what the prism will look like this. I think the camera. This is the prism. I'm holding it. Okay, fine. There's a prism. So there's a triangular prism. Like this, we'll get the different types of prism. Basically, our syllabus will be based on the triangular prisms only. If you look at the different types of prisms, so we do get the square prism, rectangular prism, pentagon prism, hexagonal prism, all that one. The triangular prism is what our syllabus. So just I showing the triangular prism here. So the prism will appear in this particular way. Then we have brought the idea of the prism. Then we introduced the idea of the prism, refracting faces, refracting edge, angle of prism. Then immediately what happened? What is the use of this prism? Why do we use? Just only to split the light into its components and to change the direction of path of the ray of light. These are the major two purposes. So first we'll focus on how to change the direction of ray of light. So when a ray of light passes through a prism, we'll undergo deviation, and we brought expression for deviation. And as I vary the angle of incidence, the deviation is going to vary. We had a plot of graph where we had the minimum and maximum deviation. We brought expression for minimum, maximum deviation. What is the use of minimum deviation? Minimum deviation you can measure in the lab. Angle of prism you can measure in the lab. So now with the help of these two, it will be very easy for you to measure the mu of a prism. We brought expression for mu as mu of prism equal to sine of a plus delta minimum by 2 by sine of a by 2. Like this, we had the expression for the refracting of prism. I can measure the angle of prism and I know the minimum deviation I can measure. So we are able to measure the refractive index of material of the prism with the help of this experiment. Then the maximum deviations we brought it here. One angle of incidence at which it is equal to 90 degree and the other angle is equal to emergent angle. We brought expression for E. Then condition for no emergence. A should be greater than angle of prism if it is greater than or equal to 2 times of critical angle for the material of the prism. Then the emergent ray will not be there from the emergent surface. So this is about the basic theory of the prisms. So in the coming classes, we'll explore the numericals based on this. Okay, thank you all of you. Take care all of you. So we'll meet in next class. Okay, bye kids. See you.